Hi everyone, I'm Kenneth, and today I'm making free videos that teach quality engineering step by step so that you can build real skills without paying any expensive course. So right now we are going to talk about the quality philosophies and foundation. Today we're going to walk through about the entire field of quality engineering. So where the ideas came from, who created them, and why they still matter in every factory, hospital, airline, and software company today. So let me start by framing why this matters. So quality means different things to different people. A customer, a factory manager, and a hospital admin. So they have different description of what is a good quality. So, but it is one of the most consequential ideas in the modern business because getting it wrong, it can cost like money, reputation, and oftentimes it can cost someone's lives. So, getting it right is what separates companies um, from other businesses. So, in plain terms, quality is about doing the job right, consistently, even when no one is checking. So, Henry Ford, if you've known him, it's one of the quality gurus here. He mentioned that quality means doing it right when no one is looking. So that's the plain language of quality. Like it's the heartbeat that we'll cover for this topic. So on the technical side, this slide is more about the history as well, like where it starts from Walter, the invention of control chart, moves to Deming and Juran's post-war consulting work in Japan and right now we have the ISO 9001 certification, Six Sigma, and Lean Six Sigma as the dominant framework for the industry. So the roadmap is like we'll pin it down and how we look at Six Sigma level, the statistical measure, and how much practice can we do for comparison. And thirdly, as I mentioned, how the history evolved. And the fourthly is the profile for three individuals who were responsible for the quality discipline. Okay, so I will not talk much more. That's the introduction. Okay, so what is quality? So in a plain language, before we get technical, so quality means doing the job right, even nobody's checking. That's what Henry Ford's definition, and the most intuitive one. But also, there's a catch. It's not one fixed rule. A customer judges a quality by whether the product solves the problem. So a factory sometimes judges a quality whether the part meets the specification. Let's say for hospital, it judges the quality by the patient outcomes and safety. So all three are talking about quality, but they mean different things. So from its core, they have a converged same fewer ideas, like fewer mistakes, less waste, and also a product service that is reliable, does what people expect it to do every time. So if you want to be technical, we can go from the ISO context, like quality means in what's on the screen. The quotation is like in section 3.62 from ISO 9000 It says quality is the degree to which a set of inherent characteristic fulfills requirements. Meaning it's deliberately broad because ISO wants one definition that works for a bolt, a bank, and a surgery. So it's worth knowing that this ISO definition actually competes with two other famous definition in the field. Like for example, for Joseph Juran defined quality as a fitness for use. So in other words, does it actually work for the person using it? Another proponent saying that for Philip Crosby, he said, on the other hand, like quality is a conformance to specification. So did we build exactly to the drawing or to the spec? So to the sheet. So these are not the same thing. So a product can conform perfectly to specification and still not be fit. for use if the specification itself was wrong. So that tension between like we build it right and we build the right thing comes with the constantly in quality work. So now how do we actually assess quality in practice? So that's where Garvin's dimensions come in. David Garvin identified eight dimensions back in 1987, and Donald Montgomery later added in three more specifically for service and transactional organizations, so bringing the total to 11. So on the screen, I'm showing four as examples. So performance, let's say for performance, does it do what it's supposed to do? Reliability. Does it keep working over time without failing? Durability. How long does it last under wear? And aesthetics. How does it look and how it feels? So the other seven, which I'll just mention here, are like for example the features, the serviceability, how is it easy to repair, the perceived quality, the reputation or brand or the impression, the conformance to standards, and then the three Montgomery added for services. Like for example, the responsiveness, the professionalism, and attentiveness. So together, these 11 dimensions give you a practical checklist anytime that you're asked, is this a good quality? So instead of guessing, we can walk through each dimension and score it. Okay. So this is one of the favorite slides to walk through because the numbers, generally surprise people. So let's start with the plain language point. So let's say 99.74% good sounds fantastic, and that's a Three Sigma process. And 99.9998% is good, so that's Six Sigma. So it sounds barely different on paper, so just a few nines. But what happens when you apply it to a tiny percentage gap to a real high volume systems? So we can walk through a couple of these three rows with me. So at three sigma, we see that 5,000 incorrect surgical operation every week across the healthcare system. At six sigma, the that number drops to 1.7 per week. So same idea with prescription, 200,000 uh, wrong prescriptions a year at 3 Six Sigma versus just 68 a year at Six Sigma. So, or look at like for example at air travel, at 3 Six Sigma, you have a two short or long landings at most major airports every single day. At Six Sigma, that becomes one bad landing every 5 years. So that's the plain language takeaway. So a gap that looks like a round error on paper, 99.74% versus the 99.9998%, is actually um, have a difference between the routine, the repeated failure, something so rare that it barely registers. So now for the technical side, this is the table 1.1 from the reference material of Certified Engineer Handbook from ASQ. And it's exactly why the Six Sigma methodology sets the target at 3.4 defects per million opportunities, abbreviated as DPMO. So instead of just aiming to be mostly right, Three Sigma performance at 99.75% good sounds like an A plus, in school. But if we can multiply that error across millions of transactions, mail pieces, prescriptions, surgeries, flights, and you get thousands of failures. So that multiplication effect at a scale is precisely the gap that Six Sigma as methodology exists to close. So it's also why quality professionals talk in Six Sigma levels rather than percentage, um, because percentage hide how the detail risk really is at scale. And so we're going to walk through this timeline again to appreciate the quality engineering. So from left to right, because the story of the quality is really the story of six turning points. First, the 1900s. Before this, quality was entirely in the hands of individual craftsmen. A blacksmith or a carpenter controlled every aspect of their own work. Then Frederick Taylor introduces scientific management, which breaks work into smaller units and moves a quality checking away from the craftsman and onto the specifically trained inspectors. So this is the beginning of the mass inspection. Like the workers stop checking their own work and pass it downstream to someone else to catch mistakes. The second is the 1924. So this is the real birth of quality engineering as a discipline. So Walter Shewhart worked at the Bell Labs and he invents the control chart. So before this, there was no reliable way to tell whether a process was behaving normally or whether something had actually gone wrong. So Shewhart chart made that distinction visible on paper for the first time. So thirdly, the 1940s, the World War II. Suddenly, the poor quality products could cost soldier lives, and hundreds of American companies were mobilized to manufacture extremely tight tolerance. So techniques like, for example, the acceptance sampling and the control charge, which had already been encouraged before the war, and it becomes a mandatory as part of the defense effort. This also when Deming and Juran established their professional reputations. At fourth, the 1950s, it's the Japan rebuild. So Deming and Juran both traveled to Japan after the war and teach statistical and managerial quality methods to Japanese industry. So this is the seed that later grows into, Japan's reputation for manufacturing excellence. So remember, made in Japan. So was the originally mark of the cheap, low quality goods, and this is where that reputation started to turn around. On the 5th, in 1987, two big things happening the same year. ISO publishes its first quality management standards, the ISO 9001, 9002, and 9003. So giving the world a common international language for quality systems. And separately, Motorola launches its Six Sigma initiative, which will go on to become the dominant quality methodology worldwide. And finally, the 2000s onward, the Lean and Six Sigma, which had developed somewhat separately, merged into what we now call the Lean Six Sigma. And quality thinking expands well beyond the factory floor into healthcare, financial services, insurance, and utilities. So the arc here is craftsmanship to inspection, to statistical control, to wartime necessity, to global knowledge transfer to international standards, so to today's blended methodologies. So let's talk about Walter Shewhart. So the engineer who arguably started this entire field. So in plain language, Shewhart was trying to solve a practical problem. So every process, like for example, a machine, an assembly line, even a person doing a repetitive work, it naturally wobbles a little from one output to the next. So the question is, how do you tell the difference between that a normal everyday wobble and needs a real problem that needs fixing? So before Shewhart, people didn't have a rigorous way to answer that. So his answer was the control chart, which at its heart, it's just simple line graph with an upper boundary and lower boundary. So as long as your data points stay inside those boundaries, the process is behaving normally. The moment a point goes outside or you see a suspicious pattern, so that's a signal something has changed and needs investigation. So it sounds simple, but it turned quality from something people argued about and guessed into something you could literally see on paper and make an objective decision from. So now the technical detail, like the Shewhart introduced the process control chart in 1924 at the technical memorandum while working at Bell Laboratories. And he fully formalized the theory in his book 1931, The Economic of Quality of Manufactured Product. It's still considered a foundational text in the field. So his key theoretical contribution was distinguishing between what he called the chance causes, now usually called the common causes. So the natural, the expected, every process, has assignable causes and now called the special causes. So it is a variation from something specific and fixable. So like a broken tool or a new batch of bad material. So that distinction is literally the statistical foundation that all the statistical process control or SPC is built on. So in recognition of his contribution, Shewhart became the first honorary member of the American Society for Quality in 1947. And today, Shewhart Medal is considered the American Standard Quality as the most prestigious technical award as of 2016. So only 67 people had ever received it. Okay. So next is W. Edwards Deming, probably the best known name in quality management worldwide. So in plain language, Deming's big, somewhat radical idea. So when he said that when something goes wrong with quality, don't start by blaming the worker or on the line. In the vast majority of the cases, the real cause is the system that management put into place. So the tools people were given, the training they received, the process they were told to follow, if a worker was not given the right equipment or clear instruction, it's simply not fair or effective to blame them for the defect. So he took these measures to Japan in the early 1950s, at a time when Japanese industry had a global reputation for cheap, low quality goods recovering from wartime devastation. So his teaching on statistical thinking became so influential that it's a major reason made in Japan transformed over the following decades from a punchline into a mark of excellence. So his core message to management, in a sentence, give people the right tools, training, and materials, and quality follows almost automatically. So technically, here's what he said. Deming held a roughly 85% of quality problems are caused by the system. Things outside the worker control, and only about like 50% are attributed to the employee. He used the Shewhart statistical quality control to help organization separate the special cause variation, the erratic, the fixable problems from common cause variation, the everyday noise built into any system. He is also known for his 14 points, a set of management principles for transforming an organization toward quality, covering things like ending mass inspection, driving out fear in the workplace, and breaking down barriers between departments. He also described the seven deadly diseases of the workplace that undermine quality, things like overemphasis on short-term profits, on what he called the management by fear, through a personal performance evaluations. In recognition of everything he gave to Japan's post-war recovery, the Union Japanese scientists and engineers created a Deming Prize, still one of the most prestigious quality awards in the world. So, in our third pioneer, who is Joseph M. Juran, who like Deming, built his reputation in America and then took his expertise to Japan in 1950s. So, where the two of them complemented each other well. Deming brought the statistical tools. Juran brought the management techniques. So in plain language, Duran made an observation that turned out to be enormously useful. In almost any system, a small number of causes that are responsible for the majority problems. He called this a vital few versus the useful many. Originally, they called the rest of trivial many, but softened that later. Practically, this means that don't spread your effort evenly across every possible issue. Like find the handful of the costs driving most of your defects and fix those first for the biggest return on your effort. He also thought that's something that's easy to overlook. Maintaining a system that's already working well and actually improving a system that has a chronic problems are two completely different skills that require different approaches. He said that you cannot fix a broken process using only tools you'd only use to maintain a healthy one. And this is where Deming and the ISO standard get fairly abstract. So Duran defined quality in the simplest possible terms, fitness for use. So not like does it meet this specification on paper, but he said that does it actually work for the person using it? So on a technical side, the vital few observation is formally known as the Pareto principle. So named after the economist like Wilfredo Pareto, who first noticed the underlying phenomenon, though it was Juran who applied it specifically to quality improvement. Today, it's one of the it is the implemented as the standard Pareto diagram, a tool used constantly in root cause analysis. So the Duran's other major technical contribution is the Duran triology. So three distinct process: quality control, which is monitoring the correcting uh, problems like sudden problems; quality improvement, a breakthrough sequence for solving chronic and long-standing problems; and quality planning, an annual program to institutionalize managerial review and control. He first also published his first handbook in 1951. It's now in the seventh edition, if I'm not mistaken, and it remains one of the standard reference in the field. He also tied project selections directly to return on investment or ROI. So this is the idea that later became core principle in how Six Sigma projects are selected and prioritized today. So this slide brings together the four major continuous improvement methodologies used in quality engineering. So let's walk through each one. First is the technical version, starting with the SPC or the statistical process control. This is where we talk about Shewhart. You watch a process over time using a chart, and the moment it starts drifting outside the normal boundaries, you get an early warning before it turns into a real defect. Technically, SPC main tool is the control chart. So its purpose is to separate common cause variation, the expected, the everyday noise, from the special cause variation, a real problem in real time. So as the process runs, next is the TQM or the total quality management. It means that it is a less a tool and more a company-wide mindset. Quality is not just the quality department's job, so it's everyone's job. So at every level of organization, from the shop floor to executive suites, until to the ownership. So TQM is structured approach built on combined principles of Feigenbaum, Deming, and Juran. So it was the most prominent in the mid 1980s through the early 1990s. So before being largely superseded by the Lean Six Sigma, partly because the TQM, while culturally important, didn't always focus on the hard technical and statistical side of fixing the process. So thirdly is the lean. It means do the job in the simplest way possible and cut anything that does not add value for the customer. So technically, lean traces back to the Toyota production system developed by Taichi Shigeo, AG, and it includes like JIT, like the just-in-time production, where parts arrive exactly when needed rather than piling up in inventory. So mistake proofing and a strong focus on smooth process, flow, and rapid equipment changeovers. And finally, Six Sigma, which we already touched in the Six Sigma level slide. So in plain language, it's a rigorous data-driven push toward a near zero effects. So with a strong emphasis on improving the financial payback of every improvement project. Secondly, Six Sigma combines the DEMAIC methodology, like the define, measure, analyze, improve, and control. So this is where the statistical rigor and ROI-based project selection has been the dominant quality framework in global scale since Motorola also introduced this later in 1990s. So the big picture to leave with you guys is these four are not really competitors. In modern practice, organization blend them into Lean Six Sigma. The most common is the hybrid because each is strong in different place. So SPC gives you a real-time detection. TQM gives you a culture and buy-in. Lean gives you an efficiency, and Six Sigma gives you a statistical rigor and financial discipline. So let's bring this all in all together. So in for closing takeaways. So and I'll expand each one of out loud so that regarding about the slide. So first, there is no single definition of quality, and that's actually fine. So not a weakness in that field. So depending on the context, quality might mean fitness for use, as Duran said, conformance to specification, as Crosby said, or ISO definition to the degree to inherently characteristic fulfill the requirements. So different words, but they're all chasing the exact same underlying goal. Fewer defects, less waste, and higher customer satisfaction. So when you're in a room debating what does quality mean here, so it's worth explicitly picking one of these framings so everyone is aligned. Second is three pioneers, one connected thread. So Shewhart gave the field its essential statistical tool, the control chart, which let people separate normal variation from real problems. Deming took that tool and made a quality management responsibility. So rather than a worker blame exercise, and Juran built the managerial infrastructure around it. the vital few, the triology, by project improvement tied to ROI. So you can really think of it as like a Shewhart gave us the eyes to see problems. Deming told the management that they were responsible for what they saw from the arts, and Juran gave everyone to disciplined way to actually go fix it. Third, the sigma gap is not academic. So we saw this concretely with the male, the surgeries, the prescriptions, the flights. So moving from 3 Six Sigma to Six Sigma is not a rounding error on a spreadsheet. So in a real world at this scale, it's the difference between the routine expecting failure and something so rare that almost never happened. So that's worth remembering anytime someone says 99% is basically perfect at a scale. So at a scale, it's not usually no. Okay, fourth and finally, so these methodologies converge rather than compete. So they're not competing with each other. So SPC, TQM, Lean, and Six Sigma each solve a different piece of a puzzle. And mature organization don't pick just one. They blend them most commonly as Lean Six Sigma, combining real-time statistical control, cultural ownership, waste elimination, and rigorous uh, data ROI-driven improvement projects into a single coherent quality system. So that's everything I wanted to cover today. So I hope you enjoy this video, and I I bring value to our deeper individual methodologies and pioneers that it will be helpful for you. So I'll see you in the next video. Bye bye.